Welcome. This is our last video, and I mean the last video for Unit 6 and also the last video for the first semester, if you can believe that. I'll probably have some review videos later on, but for now this is it. This is video 37. It's on orbital motion, and it kind of brings together all of the concepts from Unit 5 and all of the concepts from Unit 6 into one big idea. And of course, being a space guy, it kind of is close to my heart, so just kind of bear with me on this. I would spend the entire semester on orbital motion if I could, but I can't. And so we're going to just talk about it this week. So hopefully that makes sense. Bear with me then. Okay, so here we go. Let's imagine a weird situation, because that's what we do in physics, right? So you're on Earth, not weird yet, and you have an insanely powerful cannon, of course. And you decide to haul that insanely powerful cannon up to the top of the highest mountain on Earth. So let's imagine that we have some mountain. It's on Earth, like Mount Everest, but there's no other mountains around it. And you haul up your insanely powerful cannon. And with that cannon, you decide to shoot a projectile horizontally, perfectly horizontally, out away from the cannon and out away from the local region of the Earth here. So my question for you is this: how far does it go, and what does that actually, what does its path actually look like? Well, I think it makes sense, right? That it would go kind of like so. Sorry, there you go. It would fall kind of in a parabolic path and then hit the ground. But notice something interesting. Just like this down here I've drawn. Here's your cannon that's up really high and it's shooting horizontally. Normally that path would just go like this, follow a parabolic trajectory downward until finally it hits right there. But if this initial launch velocity is fast enough, notice what happens to the Earth. This is what would happen if the Earth was perfectly flat. It would hit right there. That would be what you'd find in our range formula, right? It assumes that there's a perfectly flat Earth, which for most projectiles you can totally do that because the Earth is pretty flat in a local region. But if you get really powerful cannons, like the ones that are on battleships, they actually have to take into account the curvature of the Earth. Because look what happens. The curvature of the Earth is such that the projectile actually travels farther because the Earth continues to curve downward away from where the projectile is going. And so as a result, it continues its parabolic trajectory down. And so instead of being, let's say, right here, where the range formula would predict it, it actually ends up being right there. So if you're aiming for a target with a large cannon, you have a tendency to overshoot it just because of the fact that the Earth is curved. It's round. Obviously, this is a bigger deal if the Earth would be smaller, right? So on Mars, the curvature is much greater because it's a much smaller planet. But for us, it's still important to know that this curvature of the Earth has an effect. And so we go back to our weird situation again. Let's imagine that you amp up the volume on your launcher here. You kind of crank it up to 11 if you can. Well, let's crank it up to 8. How about? So you crank it up to 8, and now all of a sudden it launches out the projectile, and it falls and falls and falls and hits right there. Okay, notice that the Earth curved quite a bit there as it tried to make its way around. Now you, you decide that you're going to go ahead and crank it up all the way to 11 if you can. So here we go. The big guns. You try to launch it as fast as you can. Now look what happens. As it falls downward, the Earth continues to curve. And it continues to fall downward, and the Earth is continuing to curve away from it, and it continues to fall downward, and the Earth is continuing to curve, and it's falling, and it's falling, and it's falling. Boom! And it hits you in the back of the head. Because you're not very smart about physics, because you launched a cannon that was at just the right speed to hit you in the back of the head. Sorry. Now, notice what happened though. As the cannonball was falling, it continued to fall, right? It didn't stop falling, but it had enough tangential velocity, right? That's that tangential velocity from the last unit. It had enough speed to the side to avoid colliding with the Earth. So it continued to fall, but it didn't hit the Earth. And so that's what we call being in orbit. Orbit is really another word for falling all the way around some object. So I'm going to go ahead and write that here. So if we say orbit, what we really mean is falling all the way around some object. It's a weird way to think about it, but it is true. You fall and fall and fall, but you're moving so fast to the side that you don't ever actually hit it because of the curvature of the object that you're falling around. Or if you get even faster, you can get a larger orbit, like planets have larger orbits around the sun. And so they're moving so fast to the side that it's not the curvature necessarily, but it's the fact that they continue to fall in a stable path. And so that's what we're going to talk about now when we talk about Kepler's laws of motion. Now, the cool thing was Newton came up with the why things move in orbits. And that was really what he was trying to answer for the moon. But years before, Kepler had come up with Johannes Kepler had come up with the rules for how things move, at least pretty close approximations for how things move in orbits. So even without knowing why, he was able to figure out how. And then Newton knew about that, of course, and then was trying to use that information to help him to support his argument that it's gravity that causes it to fall around in that orbital path. And so what did Newton know? What did Kepler say? Let's take a look at it here. Kepler's laws of planetary motion. Okay, there are three. I don't know why there's always three, but it seems like in physics you always have three. You've got three laws of thermodynamics, which is a cheat because actually there's a 0th law of thermodynamics. You've got three laws of motion. You've got three laws of planetary motion. I don't get it, but it is the way that it is. So you just gotta, they don't plan it that way, it just happens. So here's the laws of planetary motion. Number one, you're never going to have to know what these numbers are, so don't panic about that. You just have to know the ideas. So as you saw, this moved in kind of a circular path. Technically, if you kept increasing the speed, the path would be more and more and more elliptical. A circle is just a special kind of ellipse, right? So it's important to remember that the path, the shape of the path that objects take when they orbit is elliptical. Orbiting objects follow elliptical paths. And for planets, the elliptical paths look like this. The thing that you're orbiting sits at one focus. So a focus, remember, is like if you have the center of the circle, you have one point that's at the center of the circle, right? To draw an ellipse, you split that one point into two, and then you draw the ellipse around those 2 points. And so these focal points are the points that the ellipse is drawn around. And the sun always sits on one of the focal points. The other focus is just empty. It's just a mathematical point. So with the object being orbited at one focus. I hope that makes sense. It's kind of a weird idea, but it is important to know. Now, technically, that's an approximation, but it'll get us there. It'll get us to where we need to be. Oops, one focus. There we go. Okay, so here's the diagram we're looking at here. So you can see the sun is sitting at this focus, and that the other focus is empty. There's nothing there. And the planet is following an elliptical path around. Now, for planets, typically their elliptical paths are not quite this eccentric. They're not this flattened, right? The Earth's is extremely close to being perfectly round. In fact, that's one of the big arguments for why the fact that the distance from the sun doesn't have anything to do with whether we're in summer or winter. The other part being, of course, that half of the planet has winter and the other half of the planet has summer. It doesn't make sense that being closer to the sun would cause half of the planet to have summer and half of the planet to have winter. It doesn't work that way. In fact, just to prove a point, the northern hemisphere is actually farther away from the sun during our summer. So it's just weird that it happens that way. But the difference is very small. So really, we're not talking about any great difference. Uh, Pluto had an elliptical orbit, somewhat like this. But remember, Pluto got demoted from being a planet, and part of the reason for that was that its orbit was so eccentric. Something weird must have happened to it. So anyway, they should be, for planets, they should be elliptical paths, but they shouldn't be too elliptical, if you get my meaning. Anyway, so that's Kepler's first law of motion. Kepler's second law of motion says that objects speed up as they get closer to the object they're orbiting and slow down as they get farther away. This is not anything pretty crazy. But he called it this. He made it more mathematical. He said that planets or anything orbiting sweep out equal areas in equal times. And so let's go back up to our diagram there just to make sure you understand this here. So let's say it takes 1 month to go, oops, there we go, to go from E to F. And it takes 1 month to go from A to B. Notice that it's going slower here and it's going much faster here, so it covers a greater distance over here. But the areas that he was talking about were the areas between the sun and the line of the object being orbited. So if you were to figure out how much area is in that little shape right there, and then figure out how much area was in this shape right here, you would notice that that area and that area were equal. So how much distance does it travel? Well, enough to make the area equal for each month. So if this is 1 month, this area has to be equal to this if that's another month. And then if this is another month, right here, that area has to be equal as well. And so all the main idea for it is that objects, as they get closer to the thing they're orbiting, they speed up, and as they get farther away, they slow down. This is important for comets, for example, which have hugely eccentric orbits. And so as they get closer to the sun, they get faster and faster and faster, and then they get kicked back out, and then they get slower and slower and slower. It sometimes takes thousands of years to get out back to where they get to the sun again. The last one is the most important in my mind here, and that's the idea that there is a relationship between the time that it takes to go around its orbit and the average distance it is away from the object it's orbiting. And so here's the simple formula that's on the formula sheet for you. It says the average distance it is away from the object it's orbiting, let's say the sun, cubed, must be equal to the time that it takes to go around that orbit squared. And this is a kind of simplified version for the sun specifically. And if we're going to use this formula right here, we have to keep one thing in mind. So just keep this in mind for a second here. So first again, that's the average distance it is away from the sun cubed is equal to the amount of time it takes to orbit the sun squared. Which is weird, right? It's weird that that is true, but Kepler came up with a lot of different formulas, a lot of different graphs, and this is the one that worked best. And you can see, here's the graph right here. This is on this axis right here, this is our r cubed, and on this axis here, this is our t squared. And look at that beautiful, almost perfect positive direct relationship right there. It's almost perfect. Actually, technically, Mercury is not on there, and Pluto is all goofy as well. And so they've kind of simplified it a little bit for you, but you get the idea. Now, this only works in this format if you do a couple of things to cheat a little bit. The first thing you do to cheat is right here. So one of the ways that we can cheat is we can set relative distances. And so the way that we do that for this is that we're going to talk about all the distances for each of the planets in something called AU. And AU stands for not gold like in chemistry, but astronomical units, which is basically the same as saying the distance the average distance between the sun and the Earth. Um, and an astronomical unit, I think, is 1.5 times 10 to the 11th meters, roughly, something like that. Um, but instead of using that horrible number in there, we're just going to use 1 astronomical unit. And then the time, we're going to measure right here. We're going to measure that in Earth years. So look what happens. So for the Earth, the average distance it is away from the sun is 1 astronomical unit. So that's 1 cubed. The time that it takes to go around the orbit is 1 year. So that's 1 squared. 1 cubed equals 1 squared? Of course it is. So that totally works. But then you can plug in anything else you want. So if you know how far a planet is away from the sun in astronomical units, you can figure out how long it takes to go around the sun in years. Again, that's Earth years. So just keep that in mind. So this formula gets much more complicated if we want to take years and astronomical units out of it. Don't do that. We're just going to leave it in the simplest form for right now. You might also see it written like this: r cubed over t squared equals k. K is just a constant, Kepler's constant. But for k for the sun, if you use astronomical units in years, k is just 1. So there's no point in using that format if you don't need to. Anyway, let's stick with this one, and we'll remember that it's only when we're talking about the sun is this true. If we're going to talk about Jupiter and its moons, we have to reconfigure how we do this just a little bit. Okay, real quick. So we talked about what an orbit is. We talked about that they follow elliptical paths, and that the sun is located at one focus. And we talked about the fact that they speed up as they go around and slow down and speed up and slow down. And then finally we discussed Kepler's third law, which is the mathematical relationship between the distance it is on average away from the thing it's orbiting and the time that it takes to orbit. So hopefully that makes sense. I know a little bit longer, sorry, but it's the last one. If you have any questions, please let me know. Thanks for watching.